Okay, in this problem, we're going to be applying the divergence theorem again. So we're given a region of integration which is just a cube, but it has some missing corners. So basically, we have taken out a chunk of this entire cube. Now the vector field they're giving us is x, y, z, and the idea is to find the flux across the entire surface. So we're going to have f dot ds. And if we use the divergence theorem, we just take the volume E, and now we have the divergence of f dv. Now, you'll notice that if we were to use the regular flux integral, what we would need to do is we would need to define this every single surface. So this would be a surface, this would be another one, this would be another one, and then we have another one here, another one there, and so on and so on. So we have a lot of surfaces. We need to add all those results together. Now obviously that would take forever, but what we can do is we can take the divergence theorem, and this is actually going to be quite interesting because now we have a surface that is kind of cut away. So how do we deal with that? Well, we know that according to the divergence theorem, what we're calculating is for an entire volume is essentially just the total flux on each point inside of that volume, and then we're just adding that together. So the triple integral represents the sum of every single point there. So we have the flux on infinitesimally small spheres, and all that added together gives us the total flux across the entire surface. In this case, what we have is, if we look at the coordinates here, we have a cube that has length 2. So it has length 2 on every single side here. But then we notice that this is missing a corner, and this corner has length 1, 1, and 1. So that's another cube. So we have subtracted a smaller cube that has length 1, 1, and 1 to give us this entire cube here. So we have the cube. Let me just draw it. So we have this here. So we have something like this. So you get the idea. So we took that away. Now, if we were to compute the essentially the divergence of each of these cubes, so let's say this is E1. So we have the sum of all those little divergences inside. Then we subtract the triple integral of this second surface here, or the second volume rather. Then we should essentially get the divergence, or just the flux of across the entire cube. That is the shape that we're interested in. So this would be divergence of f dv. So that's an interesting concept. We can actually take the flux across each of these shapes. We subtract those fluxes because essentially it's basically like calculating the total flux here. But then we subtract the contribution of this little cube, and that gives us the total flux here. So let's see if that works. First step is, of course, to calculate the divergence of this vector field. So we're given the vector field x, y, z. So now we differentiate the first component with respect to x. That becomes 1. Then the second component with respect to y, that's 1. And then the third one with respect to z, so that's 1 again. So this becomes 3. So we notice that the divergence is actually a constant at every single point. Alright, so let's see what else we have. So we could essentially just write down the whole flux. Let's write it down as follows. 3 dv. And now what we find from this is that we can easily take this out of the integral, so this becomes 3 times whatever flux we have here. And now we notice something interesting. What is this quantity here? If we have a triple integral of just 1 dv, then this represents the volume of the region E. So if we already said that we're subtracting this from that to get this volume, that essentially this is just going to be the volume of this cube minus the volume of that cube. So we can write 3 times the volume of this cube, which is 2 times 2 times 2, so that's 2 to the power of 3. Then minus the volume of this cube, which is going to be 1 to the power of 3. So now we have 3 times 7, and then this should actually become 21. So the total flux across this particular surface is going to be 21. And notice what we did here. We didn't even have to do any integration at all. We simply simplified the problem by using the divergence theorem, and we found that we could just subtract the two volumes together to get the answer. Now this only works because obviously our divergence, our scalar function here was just a constant. But you can see the power of this theorem. If we had done it through the usual avenue of using this integral, it would have taken us at least an hour to do that. But now here we just did it in a few minutes, and we didn't even have to do much for it. So this hopefully shows you the amazing applications of the divergence theorem to practical problems.